Alrighty, so welcome to the people in the room, all the people in the room. Then welcome to the people on Zoom and the people on our streaming service. So it is my pleasure today, after some sound issues, to introduce Dr. Marek Lewicki, who did his PhD in the University of Warsaw. And then he went postdocing all the way down in Australia to then come to our beautiful country and did a postdoc in King's College in London. But since almost a year, he's an assistant professor in Warsaw. I think his anniversary is next week. So he's an expert on gravitational waves, fundamental physics, and he's involved with the ION project. Well, I'm going to let him explain what it stands for, and he's going to talk to us about what it stands for and what it does. All yours, Marek.
Okay, thank you very much for the introduction. And of course, let me thank the organizers for inviting me. It's very nice to be able to give this talk to you. So, yes, the title is Ion and Edge, Search for Gravitational Waves with Atom Interferometry. Most of what I will talk about is largely based on this first paper here. This is a recent review that we produced on ion and edge physics. While the lower two are the original white papers that came out 2 years ago, roughly. Okay, so if you want to look into the details of what I'll be talking about, this first paper here is a good place to start, or at least find good references that should tackle the problem in more detail. Okay, so let's start with some motivation. So this is the current outlook on searches for stochastic backgrounds of gravitational waves. So as a cosmologist, I usually like to use the variable, which is omega gravitational waves. This is just the energy density in gravitational waves over the total, as it would be measured today as a function of frequency. And as I'm sure you know, there are quite a few experiments that are already trying to probe this background. Most notably, of course, there is LIGO, which has made some great discoveries. However, it has not seen a stochastic background just yet. So for us, this is actually still an upper bound. And well, the other experiments that are currently running are pulsar timing arrays. There are a few of them. This is just an example of an old bound from Parkes pulsar timing array that I'm showing here. And essentially, you might have heard that there were big news in this community, initially started by reports from Nanograv that it might have, well, seen some sort of excess in its data, which is not. It's of course not confirmed to be a detection of gravitational wave background, but this could be one of the possible sources for the excess, which we will of course get back to later on. But what I want to start with is some sort of outlook. So as you know, this situation will improve quite significantly in the next decade or two. So we will have successors of LIGO. The one I'm showing is the Einstein telescope. This is the European project, next generation terrestrial interferometer, which will be underground, roughly 10-kilometer length arms. But there will be improvement all over the board. So at lower frequencies, so larger arm length, we'll of course get LISA, which is already funded, and this will be a space-based mission. Yeah, so the arm length continues to increase and frequencies decrease. And then, of course, we get back to pulsar timing arrays, which, as I said, it's possible that there is actually a signal already being probed. However, there will also be improvement over the years. The SKA, as far as I understand, is being assembled, and it will also improve over the years of observation and eventually surpass the current sensitivity of running experiments. Okay, but essentially, in a reasonable period of time. So LISA, for example, is supposed to run in 2034. We'll have a huge improvement in the sensitivity in a large part of the frequency spectrum. Okay, and the several new experiments that I want to talk about are aimed at tackling, well, one of the problems that we saw before, the gaps that we will have in the sensitivity. So specifically the one between LISA and the Einstein telescope. Those experiments are called ION. So there are a few incremental updates to this. This is ION 100 and ION kilometer. This is the terrestrial version of the experiment. And then hopefully we'll have a satellite incarnation, which we called EDGE. Okay, so, maybe let me point out that the curves that I was showing, these are actually power law integrated sensitivities. So they are not instantaneous sensitivity curves. Instead, well, if we have an instantaneous sensitivity curve, so in a very simple example here, and this is the detector sensitivity. Of course, it's already converted into the abundance that I like the most from strain. And then what one does is simply calculates this signal to noise integral for a whole bunch of power law signals, shown here as those black lines. And then we take the envelope of that, well, taking the abundances of those trial signals such that the signal to noise ratio is 10. So then by construction, if a power law signal just touches our power law integrated sensitivity line, the signal to noise ratio will be 10. So that corresponds to a, let's say, discovery. So this is a good indicator of what we can actually probe in terms of a stochastic background. So now on to AON. As I said, this is the terrestrial version of those experiments. The difference between the other planned experiments that are, well, LISA and ET at least, are laser interferometers. We're thinking about atom interferometry. So essentially, this is the setup. We will have a long baseline, a vertical shaft. And along the shaft, there will be atom sources and interferometers. So basically, we produce a bunch of cold atoms. We launch them from each of those source detectors. Then LMT laser, well, which is shared between the devices, passes through the baseline. And every time the laser interacts with our packet of atoms, there is a certain probability that they will get a momentum kick and well, their momentum will increase. So basically, after a few of those momentum kicks, when the atoms go back and we measure their state, just from the amount of atoms that have been in the excited state for a given amount of time, we can measure very well what was the time of passage of the laser between the two interferometers. This is still, well, the essential principle of this measurement. And ION, as I said, was scheduled to progress in a few stages. The first one, ION 10, this is basically, well, this is actually a plot of ION 10. Because the baseline is just 10 meters, there is no space, and we are only going to produce at most 2 atom interferometers on the way. And this is, well, as you will see, it doesn't yet actually have the capability to probe gravitational waves very well. But this is a sort of prototype to test the technology. And this is actually currently being assembled in Oxford. It was funded in the quantum detectors call a year ago, I believe. And since then, work has started. The collaboration is starting to, well, to really work on this program. And in fact, the initial grant, I think, will be enough to at least start some R&D work for ION 100, which will be the second trial version, although not a whole lot of details are settled yet, and it's not fully funded, sadly. But then our hope is to get to ION kilometer in a similar time scale as LISA in the Einstein telescope would start running. As you saw already in the plot, and you will see again in just a few seconds, ION kilometer has already a reasonable sensitivity to gravitational waves, and running it in tandem with LISA in the Einstein telescope would actually be very helpful, as we'll try to explain later in the talk. Okay, but then in a few more years, hopefully we will be able to produce the satellite version of the experiment, which is called EDGE. And essentially the design is quite similar. We have 2 atom interferometers placed on satellites. And the only difference is now, since they are in space, well, we're free to choose a larger baseline. So for this particular example, it was 44,000 kilometers. Okay, and you will see the results on the sensitivity, which is of course better than the terrestrial device. So actually there are, well, it's not completely free of problems. So these are, let me discuss it in some detail, ion noise sources that we know of that could, well, would be an issue if we can do anything about them. So this is the gravitational gradient noise. Maybe let me say what's on the plot. So the green line is the instantaneous sensitivity. This is just the detector response function. And the dashed line is showing the noise we would get from gravitational gradient noise. And then the thick lines correspond to power law integrated sensitivities if we are limited by gravitational gradient noise, and the continuous one if we are not. And this is a plot for ion 100, and on the right-hand side, we have ion 1 kilometer. So what is the gravitational gradient noise? Well, the problem is that as a terrestrial experiment, this is all just happening in a vertical shaft, and the ground around the shaft is moving due to normal seismic activity. But this is, even though the atoms are in free fall, this is changing gravitational potential inside our shaft, and this will actually be a source of noise. So the way to model this is, even though we don't know the exact site yet, so we use this is the so-called new low noise model, which was actually first developed in a geological survey back in the 90s, I believe for reasons other than gravitational wave detectors, but still, essentially, the gravitational gradient noise, or well, just seismic activity, was simply measured in a bunch of potential sites for various experiments, and then a lower envelope of all of those results is simply giving you the new, that's why it's called low noise model. But actually, this is not completely, well, this is not too optimistic in that sense, because, well, at least one experiment that I know of, MEGA, I believe, actually did this measurement in their prospective site, and they found that their noise is actually even a little bit lower than the new low noise model. But still, even with those optimistic assumptions, you can see that the difference is quite significant if we are limited by the gravitational gradient noise. And so hopefully, well, the collaboration is now trying to work on various methods to try and mitigate that. So hopefully the result will not be as bad as just if we consider that noise, but the result will be rather somewhere in between the two, the full just detector response and gravitational gradient noise limited. Or maybe I should also say that the reason why ion 100 and kilometer seem to have a different noise simply just because the noise scales with depth. The deeper we go, the smaller the noise gets. Okay. So now on to EDGE, the satellite incarnation. So the idea for EDGE is that we can use a non-trivial interferometric pattern. So the pattern of shots that we produce with the laser will not be the simple one-shot one. And doing this, producing different patterns of hits for our cold atoms, what we can do is produce more narrow but peaked resonances. So the fundamental mode, say the broadband mode, if you will, is the thin blue line here. This is the instantaneous sensitivity. But then we can set up a resonance at a higher frequency, which is, as you see, more peaked. This is the yellow line, and then our resonance at a higher frequency, the red line. And so the idea is that the detector will run switching between those different resonance patterns. And this is what gives us the full power law integrated sensitivity, just spending some time on each of the resonances. And I should also mention that in the review, this wasn't featured in the original white paper, we also talked about the design called EDGE Plus, which sounds like it's an upgrade, but it isn't really. It's just a different setup for the for the satellite, because in EDGE, what is limiting, well, one of the limiting factors is that we assumed that all of the atom interferometry will take place inside our satellite. This is a more controlled environment, but at the same time, it's small. Well, we assume just 90 centimeters for the whole device. While with EDGE Plus, we assume that we can do it up to 100 meters from the device. So we can actually launch atoms out into space, which of course, you can see that it causes some potential problems. It's a much less controlled environment, but it doesn't seem like there will be, let's say, interference enough to actually cause a devastating noise, which would disable us from actually measuring gravitational waves. So this is also a valid setup, even though it requires some more study. But essentially, the uptake is that, as you see, the sensitivity is simply much better. In fact, here it's already limited by, it's limited by extragalactic binaries. In fact, the peak would be significantly lower and the sensitivity would be better if it wasn't for that noise source. Okay, so now I should mention, at least in a few words, sensitivity to binary mergers, so astrophysical objects. So in this plot, well, those are the same sensitivities that we had before. The difference is that they are now plotted in terms of characteristic strain, which I believe is more widely used when talking about binary mergers as a function of frequency again. And those various lines show us different example sources. So this is 60 solar masses, black holes. The binary has an equal mass. And as you see, well, as you can expect from the LIGO results, the collision, so this peak at the very end of each of those signals actually corresponds to the merger event itself. They would be merging at LIGO sensitivity and at LIGO frequency. Different colors give different distance to the binary, so Z of 0.1, 1, and 10. Now, so the first point to make here is you can see that to see, say, intermediate mass black hole binaries merge, we will need to probe the frequencies between ET and LISA in the future. So 10 to the power 4 solar masses. To measure the merger, we would need to run AON or EDGE. However, there is some synergy because, as you see, all of those binaries could be detected by multiple experiments. Although there is, of course, it's not the same measuring the merger event itself as it is measuring the slow in spiral of the binary. But there is some synergy there. So for example, yes, the dots show you how long before the merger the binary was emitting at that frequency. So as you see, well, the green dot is just 1 hour, but then there is a day and month and eventually 10 years. So at lower frequencies, those actually look like point sources because the binary is tightening very slowly. And so if we were running ION, for example, or EDGE at the same time as the Einstein telescope, we would be able to track the binary throughout its evolution, but still eventually see it merge in ET, although we would have, well, assuming we could do localization, we would actually know where the event will take place, which would be very helpful. We could direct other telescopes there and look for multi-messenger signals. With just LISA itself, as you see, it would be much less trivial because, well, we would have only faint sources years before measuring ET. And if the two are running at the same time, it's not obviously, it would, I should just say that it would be better to try and measure all of the frequencies, and then we would for sure have a heads up on when the event will take place. Yes. Okay, so maybe let me skip this and let's go to foreground with LIGO Virgo binary. So this is not actually a part of the review on EDGE, but this is something that we've tried to do together with Ville Vaskonen. And this concerns actually, yes, LIGO Virgo binaries, because one of the big problems is that while the detection of LIGO events was, of course, great, and we learned a whole lot about the universe from them. Now that we know that there is a population of binaries, it will, of course, also produce a stochastic background. And in fact, well, if you assume all the binaries, just using the rate of mergers that we get from LIGO, would contribute to that stochastic background, you would get the gray dashed line here, which, as you see, cuts very deep into sensitivity of those future experiments, especially the ones in mid-frequency band. And so if that was actually a limiting factor, it would be very bad for the experiment. So a lot of people are trying to think about this, and we also joined in together with Ville. So firstly, what we did is we tried to see which binaries can actually be identified by each of the experiments. That's why there is also a thick, colorful line for each of the experiment. For instance, this is the ET one. And this actually gives you the background that the ET will see, taking out the binaries that it will able to identify individually with a reasonable signal to noise, which I think for this plot was equal to 8. And the fact that all the experiments do worse at lower frequencies is again due to the fact that at those lower frequencies, the binary is emitting for longer. And so it can actually be emitting for longer than the experiment lasts. That's why at low frequencies, it's always, well, it takes more time to collect signal to noise ratio. And if the experiment only lasts for 4 years, it can actually be a significant limiting factor. Okay. So as you see, well, most of the experiments will be able to identify quite a few binaries. Sadly, not LISA, and that's because the frequency is actually quite low already. And the signal doesn't actually pass through its instantaneous sensitivity, only the power law integrated one that I'm showing here. So yes, identification of directed identification of each of those binaries with a significant signal to noise ratio does sound rather unlikely. However, that's not the end of the story. To actually tell whether a background could be seen despite this foreground from astrophysics, what we did was well, assume a toy signal, which was, again, to try and mimic the power law integrated analysis, just the power law. So this is our would-be early universe stochastic background. Then there is the foreground for binary black hole mergers. I will explain what A is in a second. We also introduced binary white dwarfs, but they ended up not really causing any sort of problem. And then in the end, of course, the instrumental noise of each of the experiments. And then we performed Fisher analysis for each of the experiments using the black hole background, taking out the binaries that will be identified individually. And A actually, well, it's a measure of how well we know the rate. You remember that there's quite a bit of uncertainty on the actual foreground that each of the experiments will see, and that's just coming from the rate that we currently know from LIGO, but we will know it much better, presumably, by the time those experiments run. So yes, there are 3 lines for each of the experiments. The dashed line is the usual power law integrated sensitivity. The continuous line is the overlay of the power laws that we know we will be able to measure. So essentially, we will know that this omega is different from 0 for those power laws. And finally, there is a third line, which you can see in LISA, although the plot is quite busy. This is the dotted dashed line, which assumes we will have the black hole binary foreground, but we will know the rate much better. So the uncertainty on the rate was decreased by 10 to get this line here. And as you see, it mostly plays a role in LIGO and a little bit in EDGE, which also isn't able to identify individually that many binaries. But for experiments like BBO, which well, is very deep into this foreground, it will be able to identify a huge amount of binaries. You can't even see it because it's actually exactly the same as the continuous line. Now, the small problem with that is it's not fully indicative, just as the power law integrated curve was. You can probably see this because the lines just look like they were cut. And this is because there's just one power law that's the most difficult to identify, and this is pushing up the abundance. So for Lisa, for example, you can clearly see, so this is the same as the continuous line, except this is expressed as the abundance that we will actually be able to probe. You see it jumps for a certain alpha, alpha being the spectral index of the assumed background. And of course, this happens when this background is f to power 2/3, so exactly the same as the foreground, because then we really cannot tell one from the other at all. And so this is the one most difficult to measure. Yes, and you can also see a similar pattern in many of the detectors. So this is maybe a better way to see it, because otherwise, well, it could actually happen that there is a power loss signal which is just below the continuous green line, but we could still detect it. And this is just because, well, this peak, well, is making the perception of that fact more difficult. Okay. Okay, but this is something fairly new. Yes, in fact, the paper I think came out last week or 2 weeks ago, maybe. So I will not really use that in subsequent results. So let's get over to early universe sources. So of course, the big hopes concerning early universe cosmology and gravitational waves are coming from the fact that gravitational waves decouple basically almost immediately after they're produced. They interact very weakly. And so no matter the time of the production, they would still just propagate towards us and we can measure them. While previously available light-based techniques would only work since since recombination, because before that the universe was filled with plasma which scattered which scattered electromagnetic signals. Okay, in this plot, well, it's assuming that primordial gravitational waves are coming from inflation, and this is in fact the only case that I will not really talk about a whole lot, instead focusing on all the things that are possible throughout this period when the universe is still radiation dominated. Okay, so first thing, first order phase transitions. So to very briefly describe what we should have in mind, when thinking of first order phase transitions, let's think about the case of the standard model. So we have the Higgs. We know that it is breaking the electroweak symmetry. So there is a VEV, which is non-zero. That means that the minimum of the potential is not at zero. However, in the early universe, temperature corrections typically modify the potential in such a way that the symmetry is actually restored. So you can see this in this very simple example. Well, in high temperature approximation, which at high temperatures is quite reasonable, you see that the first term, even by dimensional analysis, will just be t squared phi squared. And this of course means that at high temperature, the potential will be pushed up. And this is indeed how, well, this toy model potential would look at a very high temperature. But then as the temperature decreases, this will become less and less important. And eventually the second minimum will develop. So the critical temperature, so-called, is when the two minima are actually at the same level. And the key thing here is that, as you see in this model, there's still a clear barrier between the two as this happens. This means that later on, as the temperature continues to drop, as time goes by, we'll be in a situation where we have a field which is stuck just due to its initial condition in this false vacuum at zero, but there is a lower energy configuration, which the field would actually want to go to. And the way this proceeds, and this is why it's a first order phase transition, is because it proceeds through tunneling through the barrier. So this is what I was trying to capture in this next plot, which is again the potential as a function of phi. Well, this is the configuration of the field phi, just as a function of the normal radial variable. So what we're doing next is we're just thinking of a spherical region. R is just the radius starting from some chosen origin of the coordinates. And we're thinking of the configuration of the field inside that sphere. Yes, because basically what will trigger the transition is that the fluctuations are large enough that in some region the field will be able to reach beyond the barrier. And this is what you see here. In a certain radius from our chosen origin of the coordinates, the field actually gets to, well, in this case, for the green potential, the solution is such that the field actually reaches the deeper minimum already. And then far away from the origin, it goes back to the background, which is still at phi equal to 0. And those are different solutions for different potentials. But essentially, those are so-called critical bubbles. So the sphere is at least big enough such that it won't collapse back, right? Of course, if the amplitude was smaller, for example, not reaching through the barrier, then these fluctuations will just dissipate, continue oscillating. But if it's large enough, it will not decrease anymore. It will actually start to grow because it's actually energetically favorable for it to continue converting the vacuum. It's just the energy stored in the field profile itself that is trying to stop it from doing just that. Yes, but if we start with a critical bubble, what will happen next is that those bubbles will start growing. So, okay, this is how the transition proceeds. Of course, as the bubble is growing, it's not really producing gravitational waves. It's very symmetric, so it's not a very good source. But eventually, at the end of the transition, those bubbles will start to collide. And this is when, well, the interesting things will happen. Well, actually, also growth of the bubbles is quite interesting by itself. A lot of people were working on interaction of the wall with the plasma. What will the velocity of this expanding wall be? And so on. Sadly, I don't have time to discuss this in any detail. But I can tell you some very broad, let's say, parameterization of the transition event. So the very typical variables that you'll see in the literature are, first, there is alpha. This is the strength of the transition. This is just given that by delta V. So the difference between the two minima and the potential. So just the energy, yes, vacuum energy, you would say, that's taking part in the transition over density of the radiation background. Yes, so this is essentially the ratio of the energy that's taking part in the transition over the total radiation that we've had before. And the second parameter, which turns out also to be very important, is so this is just physically the average radius of the bubble, of all the bubbles at the time when they collide. So people quite often describe this through this beta over h parameter, because beta, this is the inverse time scale of the transition. And so when you're computing the decay rate itself, it's actually quite, well, in a lot of cases, easier to compute beta. But actually, you see that there is a very simple connection between the two. And this is, in fact, the physical variable that we are interested in for gravitational waves production. So, of course, if the bubbles are nucleating very slowly, if the decay rate is somehow suppressed, they would grow to be big. And so this, well, you can think of this as R over 1 over H, meaning that this is the fraction of the horizon that an average bubble takes. So this, of course, cannot be a very big number, right? If this was equal to 1, that means that bubbles are horizon size, and then, of course, percolation will not really be possible. We need quite a few bubbles to nucleate such that they can really fill the vacuum. And so this is usually a very small number. In fact, in very strong transitions, this is at most 0.1 and usually much smaller. And yes, okay, we will see why those two are important later on. But first, let me tell you, well, about the ongoing debate of what is the most, well, the most important signal, what is the most important mechanism of producing a signal in such a transition. As I said, there is a large debate on what happens when the bubble is actually growing, essentially concerning what does the plasma around the bubble do, what is the friction that it exerts on the bubble, and so on. Well, I don't have time to really discuss this in detail, so I produced a very long series of papers that were trying to tackle the problems. Well, it starts in the 90s, but quite a lot of the developments are very recent, because this is a debate which is really ongoing, and people are, well, the results are changing significantly. Well, as recently as 2 years ago, there were, and even last year, there were significant changes. But essentially, there are a few sources, and the reason this is important is because each of them would actually look differently. So this is one of the extremely rare situations where all three of them play a role. More typically, you would find that one of them just dominates the signal. Well, either is being collisions of bubbles, so just the, let's say, vacuum configuration, or sound waves and turbulence, so things related to this interaction with the plasma. But as I said, the point is that each of those actually has a different frequency spectrum. So we could actually identify what is the source of, what is the mechanism actually producing the spectrum if we see one. So this is one such example in a model, which is a U1 B minus L model. This is really not very relevant. The only reason I'm showing this is to show you that the spectra look differently. So for example, this is a bubble collision spectrum, the dashed line here. The dotted line is the spectrum from turbulence, and the dotted dashed line is the sound wave spectrum, at least according to our knowledge from, I think, 2 years ago. And as I said, this is evolving quickly and people are coming up with different patterns, but still the hope is that just by identifying those powers of the signal that we see, we will be able to tell, well, at least some general things about the model at hand. Whether the transition was extremely strong and essentially just a vacuum transition, or was interaction with the plasma very important, perhaps what was the velocity of the wall. Yes, but as I said, this is clearly ongoing, and yes, so this identification will actually take a little bit longer. There is nothing final that I can say about this, other than identifying the power laws is crucial to actually learn any details about the model. So just to give you one concrete example, we'll take the simplest example, which is just the standard model. So this is the standard model Higgs, potential supplemented with a non-normalizable operator. I should probably say that in just plain standard model, sadly, none of this happens. The transition turns out to be second order. So at the critical temperature, there is no barrier. The field just travels along towards the new minimum immediately as it develops. There is no bubble nucleation, none of this interesting stuff. But there are many modifications that actually make it happen. And the most trivial one, perhaps not too realistic, but the simplest one by far, is just by introducing one non-normalizable operator that changes the potential, which turns out to be large enough of a modification to actually produce some barrier such that the transition is first order, depending on this value of lambda. So of course, the smaller lambda is, the more we modify the standard model and the stronger the transition, which is what you see here. This is actually the smallest lambda for which this works, 545. Below that, it turns out that the transition doesn't proceed at all because the barrier is too big, which is of course a different problem. But then as lambda increases, we go back to the standard model result. And as you see, the spectrum quickly gets weaker and weaker. Now this is the signal to noise ratio. This would correspond to at different experiments. So as you can see, ion itself would not actually be a very good probe for this model. This is in fact a very good propaganda plot for LISA. One of the reasons why people continue to think that LISA is, well, perhaps the best device to look for those phase transitions is exactly this. If we modify the standard model in a sort of minimal way, we naturally have the transition occurring at a similar temperature to, well, the electroweak scale, roughly 100 GeV, and that just happens to give transitions around the LISA frequency band. However, in general, there are a whole lot of models, and the transition can happen at any temperature, really. It won't necessarily be the electroweak phase transition. Postponing that poses some theoretical problems, although it's not impossible. But the very general, say, dependence of all of those spectra on the parameters at hand are, so the abundance of the peak, is simply proportional to alpha over alpha plus 1. This is why it's called the strength of the transition. But essentially, remembering that this is just vacuum energy over radiation, this just corresponds to vacuum energy over the total. That's all it is, and that's why this is what's modifying the initial abundance of the source. And secondly, the length scale is important. As you remember, I said this can actually be very small, and of course, this is something that would kill the signal. In fact, the weaker a transition is, also the smaller number this becomes. So essentially, what we really need are rather strong transitions where the barrier is big and the bubbles nucleate rather slowly, such that we wait in the false vacuum quite long. The energy of the transition is large. The nucleation rate isn't too big, so the bubbles grow very large, and then we will have a very large signal. Now, the dependence on the peak in terms of the frequency is actually also quite simple. So firstly, of course, it depends on the length scale. Smaller bubbles mean smaller wavelengths of the dominant source, and so slightly higher frequency. So this is why HR ends up here. And the second thing is, of course, just so this proportionality to T just comes in through the fact, yes, that the maximal possible wavelength is always proportional to the horizon size. Yes, and this actually, at early times during radiation domination, simply goes linearly with T. So this is what's, let's say, limiting us from above. And then a slightly higher frequency is a result of having a source that is actually smaller than the horizon, right? So because this is a measure of how much smaller the bubbles are from the horizon itself. Okay, but essentially, as you see, there is a trivial dependence on two of the parameters and non-trivial dependence on the third one. So in those plots, the very generic plots, I use the trivial parameters. So temperature and alpha. Okay, I forgot to change the parameters, but as you remember, beta over h is roughly 1 over this, 1 over RH. Yes, so as I said, so large beta over h means very small HR. That typically means a rather strong transition, or a super cool transition, you would say. But it also corresponds to the largest signal. So the dependence on alpha is also quite simple in all of those plots. Of course, if alpha is small, then the abundance is small. But if alpha is huge, this just goes to 1, because that just means that the entire energy of the universe is taking part in the transition. That fixes the abundance to be something, but it will not grow when that number keeps increasing. Yes, and in fact, the abundance doesn't really change with the temperature or the passage of time, because gravitational waves, the abundance of gravitational wave redshifts exactly the same as the background throughout the radiation domination period. So it doesn't matter how far back in the past this has occurred, because the abundance won't really redshift. However, the frequency will. So in general, higher temperature, of course, means higher frequency of the signal. And this is indeed SNR10 and perhaps 1, the dashed lines for each of the experiments at hand. So for those strong transitions, you can see that, of course, for very high temperatures, ET is the optimal experiment. So if we're talking about a temperature of 1,000,000 GeV or so, or even higher, then we're thinking about ET. In the standard model-ish electroweak region, so 100 GeV, it's roughly in LISA. And somewhere in the middle, so 10 to the 4, 10 to the 5 maybe, this is where ion would be the optimal experiment to look for those gravitational waves. But as I said, also just probing, well, if we have a signal peaking at any frequency, probing the power loss is also crucial to try and identify the model behind the whole event. Okay. And now on to the last topic, so cosmic strings. So to tell you what cosmic strings are, let me very briefly try to tell you what is the simplest production mechanism of them. So essentially, the setup that we're thinking of is just a breaking of a U1 symmetry. We have a complex charged scalar field. So this is U1 symmetric, and the symmetry breaks at some point. It doesn't even matter if the breaking is first or second order, but essentially this is how the potential looks like. Okay, so this was the initial configuration at some point, and then we end up somewhere in this broken phase. So of course, locally the phase doesn't matter. Along the red line, the minimum is degenerate, so locally the physics are the same, but globally it can matter. For instance, well, and it matters of course because in all of the regions that are disconnected at that time, the field will randomly have to choose its phase. So if different parts of this plot are, say, in different horizons at the time of the transition, the field can choose in a manner showed in the plot. And as you see, when those come in contact, that would mean there is a jump in the phase here because, well, of the particular choice of this phase in those different horizons. And that, of course, cannot happen. There can't be a jump in the phase. So instead, we will end up with a configuration where the field actually stays at a local maximum on that one point. And that, of course, corresponds to a cosmic stream going through this figure. And indeed, doing that thought experiment in 3 dimensions, we will end up with a complicated network of those one-dimensional objects. And the question of what the results will be for cosmology, of course, depends on how this cosmic string network will evolve subsequently. Okay, just a few minutes, so let me try and be very brief. So there is a very generic problem with redshifting of those defects, which is that they tend to redshift too slowly. Cosmic strings, the very long ones that go out of the horizon, when you stretch them, the energy doesn't change. So they would redshift too slowly. However, they are safe compared to other defects because they have an extra energy mechanism, energy loss mechanism. And this is because when they intersect, they produce closed loops. So the network is losing energy that way, and that actually leads to a scaling solution in which the energy of those infinite strings over the total just corresponds to, well, a given constant, which is Newton constant times mass per unit length of the string, which can actually be related to the VEV of the field that is breaking the symmetry. Okay, and what happens next? That's the interesting part. So when we have those loops, it turns out that throughout this evolution, they will just start oscillating and producing gravitational waves until they eventually just completely decay. So as a result, we have a very nice source which is scaling throughout the history of the universe, and it gives us this rather flat pattern of gravitational waves. So those are examples of the spectra that we get from this: G mu 10 to minus 11, or a VEV of 10 to power 13 GeV, 4 times 10 to power 13. And this gives you roughly an idea of the energy scales in question. So this goes down to 10 to power 10. So this is extremely energetic new physics, nowhere near what we can reach with the LHC. If we think just in terms of what can we probe, as you see all of those, well, because the peak also moves as the energy becomes lower, well, all of those experiments are doing reasonably similar of a job. So roughly 10 to 10 GeV can be probed with ET, EDGE, and LISA. There is actually one more very interesting thing about this, which is, as I said, cosmic strings can actually fit this nanograph excess quite nicely. This is actually the fit that we did, just assuming that the signal from strings is a power law in this very small part of frequencies where nanograph actually gave its data. And we fitted what would actually, what could be the source of the nanograph excess. And as you see, it turns out that G mu there is quite large. It's, well, up to 10 to minus 10, which actually people used to think is excluded because of those previous a little bit too stringent constraints. But as you see, the spectrum would be very strong. And the reason this is interesting is because we can use this to probe the expansion rate. Essentially because, as I told you, in radiation, the strings scale. And so, in fact, if you just had a pure radiation domination, the spectrum would be exactly flat. This means that all of those features are actually coming from the expansion. I don't know if they are too visible because the, well, integration over time actually eludes this a little bit, but there are two small steps somewhere here, and they actually correspond to a change in the number of degrees of freedom of the standard model. And in fact, this peak that we always see at the lowest possible frequency, this is just coming from the recent matter domination. And well, this fall off is caused by, well, the signal would have to be produced in the future. So this is just history of the universe, let's say, put on a line. And again, the frequency of the cause of each of those effects is just linearly going with temperature. So yes, let me actually show you. No more introductory slides. So a very simple example of that. Let's just change the number of degrees of freedom in the standard model. To make it more visible, well, for this one plot, the black line shows you what would happen if the number was fixed. And this is, as you see, a zoom in from the previous plot to see, because the abundance doesn't really change that much. But it would be, well, if the signal is this strong and we have a good handle on the actual abundance, this would of course be observed, a step big enough to be observed. Okay, but then we add, say, 100 new degrees of freedom at a given temperature. So for the blue line, it's 100 MeV, then 1 GeV, 10 GeV, and so on. So you can see that at some frequency, the spectrum will just start to behave in an unexpected way. And as I said, the frequency at which that happens just goes linearly with the temperature. Okay, and of course, if we had a more dramatic modification, say a matter domination kicking in at 5 MeV, or at the time before 5 MeV, it would just cut the signal. Okay, and last slide, luckily, I think a little bit above time maybe. But what we can do to just finally assess well, in what ways we can actually probe the expansion, this is of course a function of G mu, because as you saw, the whole signal moves also in frequency with G mu. And then we can just map it onto this T delta. So the temperature at which, yes, the effect causing our shift at a given frequency would be. And through this, so this is actually, this plot conveniently starts at 5 MeV, which is BBN. So we have data up to here. But as you see, especially if nanograv was actually somehow caused by cosmic strains, using gravitational wave experiments, we could probe the expansion all the way up until, say, 10 to the power 5 GeV in temperature. So many orders of magnitude above what is currently known. But as you see, to do this, we need a good coverage in frequencies. Okay, and that actually brings me to the conclusions. So maybe I'll just, I will just put this slide here, and thank you very much for your attention. And I will, of course, be happy to take questions if you have any.
Thank you, Marek. That was very interesting. I'm sure they're applauding everywhere. So now for questions, either raise your hand live if I can see you, or raise your hand in Zoom.